Okay, please start out with that today as your warm-up. And move that up just a bit so everyone can see a little better. Okay, how many of you have plugged in a bunch of numbers? Okay, talk with your neighbors. See if you guys are approaching the same numerator, please. So, many of you, I need your attention back up here. How many of you used a different R than someone around you? Different value of R. Did you approach the same number? What is that number? 1. Okay, so this is Kendall's. Kendall has it on her calculator here, so I decided to take that and borrow that. But you'll notice she used 14 hundredths as her R value, 0.14 there. And as she increased that value for n, it approaches 1. The calculator got to a point where it just rounded it to 1. Okay? So the numerator, as n gets bigger and bigger and bigger, when r is between 0 and 1, this top value ends up becoming what? 1. How does that change our formula then? Talk with your groupies real quick. What kind of formula can we get right there? Okay. Hey, what's our new formula? If we have a sub 1 times 1 over 1 minus r, we could actually write that as a sub 1 over 1 minus r. Okay? That is the sum of what we call an infinite geometric series, which seems weird when you say, hold on, I'm finding the sum of an infinite series. Okay, so this formula changes. How does it change? Well, if r is it's actually between negative 1 and 1. If r is between negative 1 and 1, it approaches a limit. Okay, it goes to a specific point. So you can have an infinite number of things you're adding together, but have a finite sum. Okay, that seems really weird, right? Let me say that again. You can be adding an infinite number of terms, keep adding terms for the rest of your life, but you will have a finite sum. Hey, we're approaching this value, right? We just showed that we could put an infinite. N represents how many terms we have. Okay, like when Kendall had it on her display there. Oh, I think we lost it. Okay, she had 1,000 there, but with that display, we could make that. The battery doesn't die on me completely, but right, we could keep putting zeros, and you still get 1. It's an infinite. You can make n. You can keep adding to n, and you're going to get a 1 on top. That means you have a formula right here for that sum that you could actually come up with. Now that was when we put some rules on it. R had to be between 0 and 1. It'll work from negative 1 to 1. What if I changed r? Like if I said R is, greater than 1, let's make it 2. Or, I'll make it 2. Okay? Come on, I listen to Jacob. Okay? Overflow error, that's never a good thing. Okay? So maybe we get rid of some of these zeros here. Let's delete some of those. Actually, let's delete a bunch of those. Let's go to the 10th power. All right, so that worked. Let's go ahead. Oops. Let's go ahead and go to a 100th power, see if that one will work. Okay, now we're in scientific notation, right? Yeah, so we have a really, really big number on top, and when we divide a really big number by a smaller amount, you get you still get a big number. Okay? When you have 1 on top and you divide by an amount, what do you get? Small amount. So you're taking a sub 1 and you're multiplying it by a small chunk. Okay, that's the formula we're talking about today. So the sum of an infinite geometric sequence. Go ahead and look at page 233 of your student journal. And please note what it says right here. Okay? Maybe make some notes to yourself below that. Okay. Hey, so the sum of an infinite geometric sequence with the first term a sub 1 common ratio of r, you have this. We just talked about that formula. But note the absolute value of r has to be less than 1. If it's greater than or equal to 1, then the series has no sum. Hey, quit talking back there. If it's greater than or equal to 1, the series has no sum because you're going to have a huge number up on top. And you're going to be dividing that by a smaller number. When you have a bigger number on top, dividing it by a smaller, you are taking and multiplying this by something greater than 1 every time. Meaning you're continually adding to it a bigger chunk. You can't approach a number. Whereas if this piece right here, if the ratio is less than 1, okay, or in between -1 and 1, then you're going to have 1 on top. So you'd have 1 times a sub 1, so you'd be taking a sub 1 and dividing it by an amount every time, meaning you will eventually approach a certain limit. Okay? What I'd like you to do is take a look at page 234, and I want you to work on problem number 1 with your groupies there. Okay? Make a nice grid for it. It'll help you to make a table for it as well. Just so we're all staying consistent on this, let's make these our axes. Make this equal to 1.0 right there. Hey, guys, let's talk about this really quick. It says, consider the infinite geometric sequence. Find the graph of the partial sums for S of n. For S sub n. For n equaling 1, 2, 3, 4, and 5. Then describe what happens to S sub n as n increases. Okay, so you could think of this. So some of you have been, some of you did it different ways. You're really just finding the sum of these. Okay, the partial sums is saying, hey, if I add a certain chunk together of a geometric sequence. So if I were to add this term and this term together, and then this term, and this term, and then graph those, what does my graph look like? Okay, so if I, like with just one term, when I add them together, I get 1/4 because there's only one term, my first term. Oops, n's supposed to be there. Okay, the sum, when I add the first two terms together, it would be 1/4 and 1/6, and 1/4 and 1/6 gives us a total of, if we're changing these to decimals, might be a little easier. This would be 0.42-ish. Okay, and we add the first three terms together, we get 1/4, 1/6, and 1/9. We'd end up with anyone have that? Bless you. 0.53. Okay? And then 4, we'd add them all up, we get 0.6. And then 5, we get 0.65-ish. Okay? Could someone put 10 in for me, please? Like the first, I guess we'd have to keep going, right? We'd have to actually figure, what would the next term be? Anyone figure out what we're going up by? 2/3. So actually, rather than do that, let's put 6 in. Okay, if we add 2/3 to 4/81, okay, or take this sum and add 2/3 to it, right? You're adding 2/3 to it and then adding that amount to it. Okay, can someone find out, let's find out this next term real quick. What's 4/81 plus 2/3? What's that? Or times 2/3, excuse me. Thank you. 4/81 times 2/3. What do we get as our next term? Yeah. 8 243rds. Okay, add that to our 0.65. That'll give us our 6th. 0.68. Okay, and we keep going. What we should start finding out is our graph will eventually get to a point. So I've actually graphed it here. Now, based on those first 5 terms, it approaches 0.65. Okay? However, if we were to apply our actual formula, the formula we came up with here a minute, we just showed that if we put the 6th term, we get 0.68. So based on 5 terms, we haven't quite reached where it's approaching. I want you to apply the formula that we use, S of n, but the sum is a sub 1 over 1 minus r. Apply that formula to that situation now. What do we end up with? A sub 1 is 1/4. We're dividing it by 1 minus r was 2/3. So we're taking 1/4 and dividing it by 1/3, which is 0.75. Yes. Or 3/4. Okay? So if we kept going, we'd eventually get up to 0.75. That's how this is working. That's graphically what we're exploring there. Okay? I don't want to spend a lot of time on that, but that's what we're doing there. Okay? And we could go through the same process on number 2. It makes it a little, you actually see number 2 a little better. By the 5th term, you actually get to that 3.75. Okay. Questions there? Make sense on graphing them? I'll graph them a little more. All right. Take a look at the next page, please. Number 3 and 4 at the top. Actually, let's do 3 through 6 real quick. 3 through 6. Now, my guess is we're not done with all of them, but we should be done with 3, I hope. Okay. Does a sum exist for number 3? Yeah. How come? Okay. Does the sum exist for number 4? No. How come?
Because r is greater than 1.
Good. No sum exists. Okay, no sum exists because r is greater than 1. I really need to grab my pencil over here. R is greater than 1. Yeah, as long as you can identify r. Yeah, don't do anything. R is greater than 1, therefore a sum doesn't exist. R is less than 1 here, so therefore a sum does exist. You'd actually have to do your formula. What did you end up with? 15, yeah. There's our formula. Here's a sub 1. Here's r. You plug those pieces in. 6. 1 minus 3/5, so that's 6 divided by 2/5, or 15. Okay, or someone who didn't talk in math class. All right, number 5 and 6. Give it a go.
Wait.
All right, let's check them. Number 5. A sub 1 is 5. R is 1/3. Therefore, if sum exists, we do 5 minus 2/3. We get 7.5. Okay, so remember, we're using our same formula. S is equal to A sub 1 over 1 minus R. Okay, so in this case, the 1 minus R on bottom is 1 minus 1/3, which is 2/3. Okay, number 6, same idea. A sub 1 is 1/2. R is negative 1/2. It's alternating positive, negative. Therefore, we have to be multiplying by a negative each time. You get 1/2 over 1 minus 1/2, which is 1 plus 1/2, which is 3/2. 1/2 divided by 3/2 is 1/3. Yes? On this one? I'll come over and check it out with you. Okay. All right. I want you guys to try number 7 and number 8. Okay, number 7 usually is the easier. Okay. In that type of problem, because you're familiar with the formula, you're plugging things in. A sub 1 is 30. R is 3/4. You do A sub 1 over 1 minus R. So 1 minus R is 1/4. You get 120. Okay. Nice. Now, repeating decimals. Write a repeating decimal as a fraction in simplest form. You guys, probably the easiest way to do this, identify what's repeating. 12. You take 12 and you divide it by that many 9s. So there's 2 decimal places. You're dividing it by 99. Okay? That is the fraction. I promise you. Put it in your calculator. What is 12 divided by 99? It gives you this, right? Now I could go through the whole process on it. Okay? Huh? Don't understand how I got 1299? I could definitely show that. Okay? I'm gonna reference you to a place here in a minute though. Okay. Hey, I will show you where to go to read about it, but I'm not going to take. I have like 5 minutes, 6 minutes with you, so I'm not going to go through that big explanation on it right now. But 12/99 reduces, right? Yeah. Becomes 4/33, correct? Yeah. Okay. Now, for okay, if you would like to read about this and like why it works, take a look at example 4 on page 438 of your textbook. They go through the process with you on how it works. They break it down using 0.24. Okay, if you want me to sit down with you and work it out with you, but they're using this formula, the formula we've been using. I personally jump right to the shortcut when I'm doing this, and I just say, hey, identify the thing that's repeating and divide it by 99. Well, divide it by the number of 9s of the items repeating. So if it was 0.3 or excuse me, 0.925, 0.925, then you would divide that by 999. Okay? There are 3 place values to divide it by that many 9s. Okay? You guys, each one of those though can be broken down back to this process here using our formula. Okay? So try it out. It's kind of a cool deal. It's something that usually would pique students' interest. It's actually something I used to just show in class just for fun. Okay, but it's right there. I'm not going to spend any more time on it right now in front of the class, though. But if you'd like to talk about it individually, I can. Okay? All right.